recognize language groups based on telecom traffic, right? So the green ones are the Flemish people. The red ones are the Walloon people. There's a couple of guys here in the middle, right? You zoom into them over there that are actually connecting both communities, right? So most people only call their own language. It's just reality, right? But there's a couple of people, probably in Brussels, that they connect multiple communities. They have a bridge function, right? So this is leading up to understanding, how you can extract more structure from the data and how you can model new processes because of that, right? So, and that's why I think graph analytics is really a new domain that's taking off, right? So, and he probably says finally, #finally, because it's been a couple of centuries in the making. Let's see here. Why is it taking off? Well, I think one of the biggest reasons why it's taken off is that there's so much data out there today that we actually have to make sense of it better, right? I mean, if you have 1 million people visiting your website every day, then at some point you're going to ask the question, what are they doing? Right? You're going to ask yourself the question, shouldn't we be looking at those click streams, right? That was the start of some of your work, right? To understand, what are they doing on the website? What are the patterns that are evolving there? There's so much more data there. We have other examples. We work with a company called Signify, which is Philips Lighting, right? They have light bulbs, right? But all those light bulbs are connected these days, right? They're connected light bulbs. They also have multiple sensors. They know how many people are in the room. They know how often the door goes open and close. The temperature. They know a lot of things, right? So they can better understand what's going on because there's more data, right? So more data leads to a requirement to make sense of that data, to understand the data, to get more insights of the data, right? And of course, there's a combination of algorithms and processes that need to be implemented, right? And I'll talk a little bit more about the algorithms, but there's an entire stream of IT and other activity happening on how to use those algorithms into bigger pipelines, bigger processes, which people very often refer to like machine learning pipelines, right? Once you understand the algorithms, once you understand what you can do with those algorithms, you can embed them into broader processes that allow you to have iterative learning and all those types of things, right? So I'll try to explain a little bit what are the possibilities today in the Neo4j world to run graph analytics. Graph analytics is not new, right? This has been happening for quite some time. In fact, most of the supercomputers that we know, from not so long ago, for example, Cray supercomputers, right? Those were graph processing machines. Cray actually made money with graph processing machines, right? Those were huge chunks of hardware with enormous amounts of memory, for those days at least, and all they did was crunch data and process graphs. Right? So this is not a new topic. And so there's been a bunch of existing options out there to kind of emulate that with software, right? So there's hardware that you can use for graph processing, but there's a lot of software out there today as well. Like for example, Spark has GraphX, Flink has Jelly, Eureka, Giraffe on the Hadoop ecosystem, Network X in Python. There's even Excel that has a graph add-on these days, right? So there's a lot of tools out there that allow you to do some little limited form of graph analytics today. By the way, you guys, you will get the slides. If you've registered with your email address, you will get the slides tomorrow, right? So don't worry about it. And very happy to share them otherwise as well. But those tools, they tend to be quite complicated, I think is the summary, right? It's quite a bit of work, and it takes a rocket scientist to really make sense of them and to really put one and one together and operationalize those types of tools. There's a lot of moving parts, and it only takes, one little typo in a config file to not make it work at all, right? So I guess what we are trying to do here, I'll speed up a little bit here. These are some examples, but this is an example actually from, this was a guy at Graph Connect last year who was doing Twitter analytics. Twitter obviously has a lot of interesting facts and a lot of interesting data, but there's also a lot of interesting new crimes being committed on Twitter, like influencing elections and stuff like that, right? So there was a guy, John Swain, who explained how he went about understanding Twitter data, and this was actually reported quite a bit on ABC News, did a whole research story around it on the Russian Twitter trolls, right? And that was because of this research. But this was his pipeline, right? And that's a big, complicated piece of software and hardware that he needed to do, right? So first, collect all the tweets with a Python script, put it onto a queue, RabbitMQ, then push it into MongoDB, then get it into Neo4j, then run a bunch of scripts on it, R scripts on it, then put some of that into MySQL for some reporting in Tableau, and then export it into GraphML to do some visualization on it. I mean, that's quite a bit of work, a lot of moving parts, a lot of potential failure points, right? And I guess this is what we want to do, right? We're trying to get to a point, and I think we have come a long way here, to make this so much easier. I mean, even I can do some graph analytics these days, and that's quite an achievement. So cutting out some of them of the intermediate steps, I guess, is the summary of this. If you've got Neo4j, you've got native graph storage. You're storing the graph as a graph, down to disk. So there's a lot less need for all of this data manipulation, wrangling, converting that you need to do. There's a lot more that you can do when you've got the data as a graph in your graph database, and you can run graph analytics on top of it. I guess that's the summary of what we're trying to achieve with our graph analytics and algorithms, right? So there's a bunch of new types of capabilities that we're building. This is not a finished offering. There's a lot of stuff happening here, and every release, everything gets a lot better. What do we have today? There's first of all, I already mentioned it. Neo4j as a native graph database, right? You structure the data as a graph, which avoids you having to convert it time again from some other format into a graph format in order to do the graph analytics on it, right? Once it's stored in Neo4j, you have a native graph, you can operate on it as a graph. Operating on it is something that you do with a query language, right? And you'll be surprised at how much you can already do with the declarative Cypher query language. Just learning, mastering, or at least getting your head around the Cypher query language allows you to get a lot of simple but meaningful statistics about your graph very, very quickly, right? Things like degree, for example, right? Which is a very important measure which is used in lots of algorithms to understand, how important is a node? How is it connected to the rest of the graph? Well, that's just standard Cypher functionality. You don't need to run any complicated algorithms on that. It's just something that you can do, out of the box, so to speak. It's something that Neo4j needs as well in order to function as a database, right? So it's got that baked in, so to speak. But Cypher, it's a declarative query language, so it also has a bunch of things that we don't know how to do yet, right? we're still working on that telepathic interface, and so we need some more guidance from users sometimes to really do things efficiently, which is why we created these APOC procedures. Right? I don't know if you're familiar with that, but since I think about 2.5 years now, you can plug code onto Neo4j that allows you to do things imperatively, right? So you can tell it what it needs to do. You don't, with Cypher, you declare what you want and it figures out how to get to that. With APOC, you tell it what to do and it will do it for you, right? It's imperative, right? But there's such a big, sorry?
You write code in which language?
In Java.
In Java.
In Java. So it's a plugin onto Neo4j. There are some ways that you can do it in other languages as well, but it boils down to Java at the lowest level. There's hundreds of these procedures these days. We compare them to stored procedures, like we call them APOC, and that's not just a character in the Matrix movie. It's also awesome procedures on Cypher. It's a way for us to get access to more horsepower by basically just calling a procedure, and it will do something for you. There's hundreds of those, and it extends that query language, and it gives you more analytical capabilities. Now, more recently, we've added 2 more things to this, and the first one is optimized graph algorithms. I mean, APOC is the start of this. It's clearly the library with the most functionality, lots of different things that you can do with it. But we've actually spun off a specific plugin for Neo4j, which is all about the graph algorithms. And they've been optimized. They've been optimized to run much more quickly. Right? They also use much better use of processing power and memory, and they are parallelized. Right? So they allow parallel execution of not all, but many of the graph algorithms. So they typically run a lot faster. Right? So there's a APOC library and there's a graph algorithm library these days that allows you to do a lot of this algorithm work, analytical work. And then, the last thing that we're doing is we're building analytics integrations, right? Because, some stuff, some data is too big to fit onto one machine, right? Mind you, you can get very, very big machines these days. But some machines, some data is too big, and then you need to distribute it across multiple machines, and we will need to integrate with other platforms that are more optimized for that, like, for example, distributed computing platforms like Spark or Hadoop or those types of environments. Right? And then we want to have an easy way to pump data out to that distributed computing environment, do the processing there, and pump it back into Neo4j much more easily. Right? The 3 main algorithms that you will find in the algorithm libraries are about these topics, right? The first is around centrality, right? And centrality is to try and understand what the... There's a camera. You should go below the camera. Centrality is all about understanding the importance of specific parts of the network, right? If I want to analyze a big graph, I'm going to try and figure out, what are the most interesting parts of that graph, and centrality is going to give me indications for that, right? Centrality can be very simple things, like counting the number of, connections that something has. It can also be much more complicated by understanding things like those bridge functions that we talked about earlier, right? Those 2 language groups, and there's a couple of people in the middle. Well, they probably have what we call a high betweenness score, right? They are between different things, right? So they become more important because of that, right? That's also a centrality metric, right? There's many different ones or many different kinds of centrality metrics. There's pathfinding algorithms. Pathfinding algorithms, you know, you probably, I don't know if some people have seen me do my beer demo at one point. You know, I have a demonstration of Neo4j. Matt is already smiling. It's about Belgian beers, and you try to find, you know, what are the paths between two beers. And guess what? The things that you find on the path are interesting beers, right? So finding paths between things can be a very interesting measure, not just by, you know, to find out of new interesting things, but also if you are trying to understand, like for example, the propagation of failure, right? And like we talked about earlier, you know, that means you have to try and find all the paths from one particular point in the network, right? So understanding paths that flow from a failure point. Or if you don't know where the failure point is, but you have a bunch of people saying, okay, there's a failure, I can try and walk from all of those, let's call them users, to each other and see where the paths cross, right? And if the paths cross in one specific point in particular, that's a good suspect for finding the root cause of the problem, right? So pathfinding is really interesting. And then Louvain, what I mentioned earlier, is an example of the third category of algorithms, which is all around community detection. Understanding what we call cliques, right, in graphs, right? Things that belong together, things that partition the graph, that divide the graph into multiple areas, right? There's lots of ways to do that, and frankly, I'm not the expert on this, but community detection is really interesting because you can basically chuck a bunch of data on it, and it will literally tell you what things belong together and what don't. Right? And it will not always be very accurate from the first go, but you know, it's something that really happens a lot these days. Right? So the way you do this, and I'll show you this in a little bit, you call these algorithms with a Cypher procedure, with an algo procedure that I mentioned earlier. Right? You give it a bunch of parameters, right? And you have two options, right? Either you stream the data out, the result of the algorithm, you stream it out, right? Or you persist it and you write it back to the graph, right? As a property on a node or as something else, right? You can do things like projection, right? So you can pass in Cypher statements, right? And then get a graph as a result of that. Right? That can be the result of an algorithm. Right? These are the algorithms. I'll skip those a little bit. PageRank, you're probably familiar with that, right? That's the Larry Page invention that founded Google, right? Betweenness, closeness, degree. We've talked about those. Those are all centrality algorithms, right? Community detection is all about, there's a lot of different ones. I'm not very familiar with them, but Louvain is the Belgian one, and it seems to be one of the most efficient ones. It's the one that works the fastest and the most accurately. And you have pathfinding algorithms, right, where you can have different ways of finding paths from one thing to another. And sometimes, things like PageRank are actually variations of this. PageRank is a variation of an iterative pathfinding algorithm, right? And you iterate on this quickly. You make sure that you can do that very, very fast, and then you can have results pretty quickly. There's quite a few examples of this, but what I'd maybe like to show you is, I'll keep this short. The pizzas will be here anytime. There's a very, very nice tool that you can use these days to play around with this and to learn how to use this, right? The one that I've here, the database that I have here, I've also experimented with my beer graph on this, but I've got the Graph of Thrones here. I don't know if you're familiar with it. It's Game of Thrones, obviously. There's a guy that analyzed all the books, the Game of Thrones books, and he's basically mapped out all the interactions between characters. So what he's basically done is he's taken the text and he's looked at all the names and he's said, you know, if a name of a character is within 10 words of another character, then that's an interaction. Right? That's an interaction of two characters in the Game of Thrones series. And guess what? Someone has imported that into Neo4j, and now you can play around with it because you can run interesting algorithms on it. Right? It's not a very big data set, as you can tell. There's only 797 characters in there, but there's quite a few interactions. Right? There's quite a few interactions between the different characters. And you can explore that just by going to your Neo4j browser, right? And the way to do that is, you know, oh, wait a minute. There's a guide that you can use. By the way, this you don't actually have to import the data. There's a Neo4j sandbox that already contains the data. But you can run what we call a guide here, right? It's a guide. I don't know if you're familiar with this. If you've used Neo4j, you know that it's got like this learning environment embedded into it, right? And you can basically go through here and you can look at the schema, right? Look at the schema of the database, right? Don't worry about this guy. That's because I've been using the new version of Bloom on it, right? So you see interactions. Now, from a modeling perspective, it's characters interacting. You know, you can get some statistics, some very easy, you know, statistics on there. Oh, what have I done? Damn it. So, damn it. I was trying to go here and pin that. But it also gives you like more interesting algo capabilities here. Like, for example, this one here, I don't know if you can see this very well. This one here at the top, it calls the algo package, right, with the betweenness function in it. It's going to stream it, so it's not going to write anything back, right? But it's going to look at the betweenness of the characters through the interacts1 relationship, right? So this is all about the first book. I'm trying to find the betweenness score of characters in the first book. You without really having to know any, you know, Cypher or procedures or anything. So this is very, very simple, right? I can just say, okay, I want to understand the centrality of a character. You know, I want to use any relationship type. I don't want to store the results, and I just want to run it, right? I can do that with any of the algorithms, the community detection algorithms, the pathfinding algorithms, the similarity algorithms, all of those are in here, and you can just use it and see what's behind it, right? So behind it is one of those procedures, right? I don't know if you can see this very well. Yeah, it's very, very small, but behind it is a procedure. This is what's being called. You can actually, there's a button here, send to Neo4j browser, and it will just run it in the Neo4j browser, I hope. Yeah, so it actually, now it creates this thing, and then I do this. It's supposed to do that automatically, but obviously I'm doing something wrong. So then you can click this thing to set the parameters, and then you click this algo, and it runs it for you. Right? So it's super simple to get started with this stuff, right? I mean, I'm not giving you any real results here. It's a way for you to experiment with this, to learn this stuff, and to hopefully get to the value of the graph algorithms a little bit more quickly. I know I'm separating you from your pizza, so I will, there's a bunch of other examples here, a couple of really interesting ones, DBpedia that you can take a look at. This is all public data, right? Yelp publishes data every year that we can run these algorithms on. You'll get this tomorrow. Bitcoin data, obviously. We have some really interesting research going in there because there's all kinds of stuff happening there. And like I said earlier, this is optimized architecture. It's something that we're trying to get as much speed from the algorithms as we possibly can. And I think, I bet you had some good results with it, right? In the initial test that you did. It seems to be something that we can really argue that it's, we did a test here on I think this was the Yelp data set on a big Amazon machine. And this is just a picture showing that we were actually using every single CPU, which is great, And we had some very positive, performance results. How quickly can you find, like for example, page rank of a specific database? It really worked quite well, and that's the native graph database. That's giving you that. So you don't even need to install it. You can go to the graph algorithm sandbox, neo4j.com/sandbox, and just spin it up and try it out. This is a beautiful picture, as you can tell. But you can play the guide of the graph algorithms, or you can install the graph app. Install.graphapp.io, and you can install it into the Neo4j desktop and take it for a spin, right? And then Neuler will come to the rescue. Pizza or first questions? Anyone has questions? Any example of community detection? Oh, there was actually. There was some of our. We have a big office in London, and we have a lot of international employees in London. So there were a bunch of people very interested in understanding what the communities were in the Brexit debacle. But there were no crazy results as far as I remember. It was basically the party lines. It was very much party lines that was splitting the community detection. But I can look that up and see if there's any. Who's Rick? Is there another Rick? Oh, that's okay. Very good. Yeah. Well, I can send it to you if you want. Shall we have a pizza? Is that okay? Or do you guys really want cold pizza? Let's have a piece of pizza. I'll be there as well, so we can talk over a bite and a drink.